Alright, what's going on, my fellow physicists? Today I'm going to be talking about potential energy and some of its forms. So, what is potential energy exactly? Potential energy is essentially just energy that is stored or ready to be used for work. To trigger this energy release, conditions need to be met. So, I went ahead and color coded potential energy in this case um, as red, and then the conditions that it needs to meet or the conditions met are going to be green. So an object that is high up from the ground on a ledge must fall to release its potential energy. So this is gravitational potential energy. I'm going to be getting into this one a little bit more later. But we see here that the potential is that it's high up. Therefore, there is, right, we're dealing with gravity here. Gravitational potential energy. And then when it falls, it is releasing its potential energy. A spring is compressed, but then is released. So elastic potential energy. A spring is being compressed by someone's hands or whatnot, and then once they release it, the potential energy becomes energy. A person consumes food and then later exercises. So this one is chemical energy. This one is really interesting because we all do it without realizing it. Anytime we eat proteins or carbs, quite literally, the macros and whatnot, we are getting energy from eating. It is not just a metaphor. It is quite literally energy, and it's called chemical potential energy, and we use it to survive, do anything, any kind of work. So gravitational potential energy is what I'm going to be talking about mostly here. So PE, or potential energy, is equal to, in gravitational potential energy's case at least, is equal to the mass of the object in kilograms multiplied by the gravitational acceleration of the planet that the object is on, right? Because it's relative to gravitational acceleration. And then multiplying that by the height of where the object is dropped, or the starting position of the object. So, this is a little question I whipped up that was kind of fun to do, so I'm excited to share this. How much potential energy did David Scott's hammer have before he dropped it from his hand on the moon? So let's see here. Keyword before he dropped it. So we know we're dealing with potential energy, right? And obviously I did state it here, potential energy. His height is about 6 feet, okay? And he dropped the hammer from about his shoulder height. I mean, at least according to the video, that's what it looked like. So we can shave off approximately 10.5 inches from his total height, because that is the approximate length between a man who is 6 feet head and shoulders. So from like the top of their head at least. So from 6 feet, I subtracted 10.5 inches and I got 5.125 feet. And so we know that the hammer was probably dropped somewhere around this height, right? So 5.125 feet above the moon's surface. And his hammer was approximately 1.32 kilograms. That is the mass of the hammer. So let's go ahead and get, mass equals 1.32 kilograms. So we already have this. This is given for the most part. We do have to solve for this. We need to make sure we convert, I just covered the number. We need to convert 5.125 feet, because physics does not like the imperial system. We are going to, I don't really like it either, I'm not going to lie. We are going to convert that to meters, because that is what we need for the equation. So let's see. So 0.3048 is approximately 1 foot. So there is 0.3048 meters in 1 foot. So let me go ahead and solve for this. 1 second. 5.125 times 0.3048. So this gives us a height of 1.5621. All right, so this is the height in meters. So now what we need is, let me see here, let me go ahead and cross this out. Just so you know, we got rid of feet, right? So just cross it out when you're doing dimensional analysis so you don't get confused. And so let's see, PE, let's write out the equation so we remember, mgh, right? So now what's left is gravity. So how am I going to find the gravitational acceleration of the gravity on the moon? So we know that gravity on the moon is approximately 1/6 of the gravity on Earth, right? So I'm going to take 1/6 and I'm going to multiply that by the gravitational acceleration of the Earth. So that's 1/6 times 9.8. And that should give us, so 1 divided by 6 times 9.8, approximately 1.63 meters per second squared, of course. All right, so now we can kind of just go ahead and throw these together and multiply them. So 1.32, oh yeah, and of course PE, and then we're going to multiply that by the height, so 1.5621, right, that was the height. And then now we are going to multiply it by the gravitational acceleration, which is about 1.63 meters per second. So let me go ahead and throw this together on the calculator. 1.32 times 1.5621 times 1.63. All right, so my final answer here is potential energy, or the potential energy that David Scott's hammer had right before he dropped it from his hand on the moon, is approximately, let's keep this approximate, approximately 3.36 joules of potential energy. And that's it. Thank you for watching, guys. I really appreciate it.